Hello, ladies and gentlemen. Welcome to Physics 20 Vectors Lesson 3, Relative Motion Navigation Problems, Part 1. Now we're going to interpret qualitatively the motion of one object relative to another using displacement and velocity vectors. So, first we have to definition, relative motion. Relative motion is motion measured with respect to an outside observer. Okay? Which means you got to read the question carefully. A fly traveling in a car buzzes at 5 meters per second forward. The car travels at 25 meters a second forward. What is the velocity of the fly relative to the observer in the car? Well, here's the fellow sitting in the car, and here's the fly buzzing at 5 meters per second. So, relative to the observer in the car, velocity fly, 5 meters per second. Notice I'm not using plus, you're assuming it's plus because it's forward. Now, relative to an observer on the street, there's somebody standing on the street. There's the fly going by at 5 meters a second, relative to the car, but the car is going 25 meters a second, and 5 meters a second. So what does the observer see? Well, he sees them added together. He sees the resultant is 30 meters a second. Okay? Now, if the fly turns around and flies with the same speed, what is the velocity relative to an observer on the street? Well, here's your observer on the street. And there's the car going past at, sorry, if we're going to do velocity vectors, let's make this to scale. 25 meters per second. And what's the fly doing? It's flying backwards at 5 meters per second. So what's the resultant the outside observer sees? He sees 20 meters a second. Okay. So far, so good. So read the question carefully. Now, a jet has an air velocity of 800 kilometers an hour west. There's a crosswind of 52 kilometers an hour south. What's the ground velocity of the jet? Well, that is somebody on the ground. What do they see? Well, they see a jet going 800 kilometers an hour west. But there's that wind of 52 kilometers an hour south. So he's seeing the resultant here. Now you notice west and south, that's right angles. So this is Mr. Pythagoras. A squared plus b squared equals c squared, or 800 squared plus 52 squared equals resultant squared. So the resultant, can't do that in my head anymore. I try, but I'm just too lazy. 800 squared is 640,000. And you notice once again I'm chunking this because so 642,704 kilometers squared per hour squared. I shouldn't be dropping my units. I am, but I shouldn't be. So the resultant, square root of answer, is 802. We'll call that 802. Now, important part is the velocity, but sorry, with velocity, there's a magnitude or amount, so I need the angle, sorry, the direction to go with it, because that's the more important part with this navigation. What's your direction? Tan theta is opposite over adjacent. 52 over 800. Angle theta is tan to the minus 1, 52 over 800. Nope, wrong one, sorry. Mode, I'm in degree, good, clear, inverse tan, 52 divided by 800. I should close the brackets out of habit. 3.7 degrees. Now, to do that, you are going, sorry, as you go west, south. Yes, 3 points. So you go west, then you swing south to make an angle 3.7. And that 3.7 degrees is important. Yeah. Because, yeah, jet can only land at an airport. You miss the airport, you're off by 3.7 degrees. You're going to miss. Anyway, now, what if the jet wanted to fly exactly west? What angle would it need to head out in to have a result ANT? Resultant of due west. Now, your first thought is, oh, go north 3.7 degrees. No. I want you to note in a problem such as this, the resultant is not the hypotenuse. What happens here? Well, let's reword the question. The same jet wants to fly directly west, and the air velocity and wind velocity, I'm sorry, remains the same. What angle must the jet start off at? What its resultant will be? So here, remember, it's going 800 kilometers an hour. And, sorry, 52 was it or 57? I forget. 52. And we want the resultant here, so it's going straight west. And this is the angle we want to find. And the resulting velocity. Okay, now note here, this is it's not the same triangle. It looks the same, but it's not. Different angles, different side lengths. Okay? And yes, you'll get a multiple choice question, and if you put down 3.7 degrees, that's wrong. So in this instance, 52 squared plus the resultant squared is 800 squared, or I can't remember. What was it? Okay. What's your issue? Come on. I don't work. One moment, I apologize, ladies and gentlemen. Mr. Calculator decided to go on strike, you poopy head. There we go. Try this again. Scrolling up. Yes, it was 2704 and 6400, 64,000, 640,000, sorry. My apologies. So that was... Excuse me. Enter minus... So that is 637,296. And the resultant, second squared second answer is 798. $798, 803. There is a difference, and if you do this for several hours, yeah, you can miss the airport or overshoot it. So, no. And we know this is going exactly west. Oh, sorry. My apologies. Misread the question. The question was, what angle? Now, that's the resultant velocity, but I forgot the angle. So that is opposite and hypotenuse, so that's sine of theta. Which is 52 over 800. Angle theta is sine minus 1 of 52 over 800. .7. 3.73, not 3.74. So it is slightly different. If you go to a couple different 3.7, yeah, you go to 2 decimal places, it's different. That's not a good example. I'll come up with an evil one. Give me a moment. All right, so let's try another one. Actually, no, let's stop here. Video's getting kind of long. We'll pause it and then, sorry, I'm going to pause it here. If you're having questions, watch the video again. And that wasn't really a good example because the angle should be noticeably different. Anyway, I'll rewrite it for next year. So here, no, if you got questions, shoot me an email. Otherwise, we'll go on to the next video. Good luck.